so happy to have our alumni, Dr. Rong-Shyang, given his job talk and also a seminar. Dr. Li graduated from our university in 1998 for the master degree, and 2002 for his PhD. Afterwards, he went to the Academia Sinica as a postdoc, working at the Fermilab CDF experiment. In 2007, he joined the Heinz group in our department and stationed at the CERN Geneva to work on the CMS experiment. He's one of the key persons for our hardware project. Today, Dr. Li is going to share his experience on CMS project, and his, the title of his talk is CMS Phase 2 Calorimeter Upgrade, Physics Prospect in High Luminosity LHC Era. So let's welcome Dr. Li.
Thank you. You hear me okay? Okay, thanks for this opportunity. So as you see my title, I want to share the project that we started towards the Phase 2 upgrade and what we expect in terms of physics. So this is my outline. I will quickly introduce what the LHC and CMS is, and then I'll describe what the silicon detectors technology that we've been working on and toward the HGCal. And then I'll end with what we expect we can do in terms of physics. Okay, for the people that have not seen enough, I will just quickly tell you that what is LHC is actually accelerator ring in the border of Switzerland and France. And the ring is 27 kilometers circumferences, and it's actually built 100 meters underground, so we have to take time to go down. And there are 4 major experiments, CMS Atlas, Alice and LHC on the ring, while I was working on the, I'm working on the CMS experiment. And LHC has been running very well. You probably have heard from some other places like news conference. And we have been running this, defined the 3 years as a round 1, and there's a gap that the LHC is opened for the maintenance. And we started round 2. And this is a plot of the luminosity where we used to calculate how much data we get, and you can see that the last year was running very well. And then just give you an idea, the Higgs discovery was found, and the conference, the press release was made on 2012. And we're expecting next year, or the coming year, we'll accumulate the same amount as last year, so it will be a lot of data. And for CMS, CMS stands for compact muon solenoid, and it's a general purpose design detectors that you can detect all the stable, semi-stable particles, so we can do wide researches. And the detector, this is the drawing, and the weight is 12,000 tons, and the dense is 22 meters long, and actually you can see there's a scale of a human that's standing there, and the diameter is 15 meters, so it's quite a large detector. And we also run the magnetic field of 3.8 Tesla. And then quickly just show students how you detect particles, that once you have a proton-proton collision happen in the center, you have all sorts of particles coming out. Then you try to make a detector that can detect it. And the easiest one to explain is the muon, because it goes through everything and escapes to the atmosphere. So what you do is you put a lot of material in front, and whatever escape, that's a muon. So that's the easiest. But then from the inside, you have the silicon detectors that I will describe and explain a little bit later, that try to measure all the so-called charged particles and measure the trajectory. And since this thing is running inside the magnetic field, so you can see that they are curving. By measuring the curvature, you know what the momentum is. And so now you can see the example that, of course, muon is the charged particle, so you get the trajectory. You also have electrons or pions, kaons, all sorts of things. You measure trajectory. Then after that, you will have a layer of ECAL, that's electromagnetic calorimeter, which I will also explain a bit later. And that will measure, you can see that electrons or photons will be absorbed, and then we measure the total energy here. And the design will not have any electron or photon escape. And the only thing comes out next will be the hadron particles, like kaon or neutrons or hadrons. So you see that by doing layers of different technology, you can cover all the semi or stable particles. And let me just mention a little bit on the ECAL, since our group is working on this, and this is the subject of the upgrade. So the ECAL of the CMS, ECAL stands for electromagnetic calorimeter, and here's the drawing that mainly have two parts. That is the barrel part surrounding the detector volume, and then two end cap discs. And the ECAL is mainly composed by the lead tungstate crystals. So as I explained earlier, you try to measure everything that is EM particle and absorb everything. And by measuring the energy, so you know what the particle is, so you measure the energies. And in front of the end cap, there are actually two layers of the sampling calorimeter, which is sandwiched by the lead absorber followed by silicon strip detectors. The idea is that because it's a silicon strip, you can have much better spatial resolution, so you can know the incident particle is a single photon or the two photons very nearby. And because the crystal has a limit on the segment size, it's not very easy, and that's where the Preshower comes in. Okay, so here is the 10 years LHC plan, and we are sitting here, as I show in the luminosity profile. We are now in the year-end technical stop, and in the round 2 running periods. And so what we'll be talking about is the high luminosity LHC. And one thing I just mentioned is that the luminosity will be much increased, almost factor of 5 more. Okay. So why we need to do the upgrade? So here is the simulation of the detector performance we expect during the high luminosity LHC area. So this is the end cap crystal response by injecting the 50 GeV electrons. As you can see, we are sort of here. Eta, you can see that's the theta angle. So if you go to forward, that you've got the drop of the light yield from the crystal because of radiation damage. And once you start accumulate more and more data, you can see that in the end, if you don't do anything, you got even 1% or less light from the crystal because they're not transparent anymore. And of course, in that case, you won't be able to do any physics. And the best way is to replace it. And similarly to the hadronic calorimeter, you can see that the degradation is a function of the theta angle and the layers. So, yeah, so the idea is to replace the whole electron calorimeter, EM calorimeter, and the hadronic part, and otherwise the resolution will be worsened. And the new detector is designed to that you have a much better granularity. So you have both angular and lateral resolution. Plus, if we do something smarter that get the timing information of the incident particles, we can help to detect to measure the particle better. Okay, so here is the drawing of the new detectors. And that's what we call the high granularity calorimeter. It's expected to be built by 2023, only 6 years from now. So we have to build everything and then install it during the shutdown. I'll go through this a bit later. And for the phase 2, of course, during design, we try to see what the performance is for the various design. That was the one was chosen eventually. But for example, that if you look at the efficiency of electrons, you can see the red one. If you do nothing, you have low efficiency. But if you replace the end cap, you will recover back to what it should be. And similarly to the, I think this is for hadrons. Okay, then I'll start explaining why silicon. So the principle, first, silicon, everybody know, is a very good matters that you can play and is rich on Earth. Actually, you go to the beach, get the grain of sand, try to purify it, you got the silicon. And it's also very easy to dope, to change the properties. For example, typically we do is you take silicon, you start doping different material. Like if you dope the boron, then it becomes the p-type. And because there's a open bond, boron has only 3 electrons outside. But if you use a phosphorus, then you got the extra loosely bound electrons. And so this is n-type. Then if you put the P and N together, that then touch each other, make a join. Because this open bond and the loosely bond, you extract this loose electron to this bond, so that naturally you attract the electron to the p-type, and then the n-type silicon become the positively charged. This is what we call the p-n junction, and you naturally create electric field pointing to this direction. And for the application, and of course, the rest of the area is still neutral. That means whatever charge electron or hole goes in will just diminish, just disappear, because they are neutral region. So what you do is you apply a so-called reverse bias to bring this E field all the way back to the end. So you create the whole material having the electric field. And the application will be something like this. This is now the so-called traditional silicon strip detector, although it's not many years yet. So what you do is you have a bulk of the silicon, usually it's 300 micron thick. Then it's lightly doped as n-type. And then you have the strip or pixel that is heavily doped as a p-type. Then you apply the reverse bias, you deplete the whole range that your material have the electric field. Once you have a charged particle go through, you create the electron hole pairs, and because the electric field inside, all these electrons will drift to the electrode here, and the hole will drift up, the electron will drift down to the back. And by playing with this readout channel or segmentation, you get to detect where the particle comes in. For example, if you read a large signal here and some here, then you know it has to be in between, and vice versa. Okay. And that was why we are using silicon. Then I'll show you a few things that we have done, and in the NTU-HAP group. This is the first detector in CMS that we have contributed and built, which is the CMS Preshower detector I mentioned earlier. So what you do is you start with the design and layout, and then send to the fab to make what we call so-called sensor wafer. Then you cut it out, but you cannot just take the silicon and say want to read it. It's impossible. So you have to apply the service. For example, the ceramic sport for both thermal conduct and the high voltage the electrical contact. And then once you build, put the mechanical support, put in the readout electronics, bond it, then you got the working silicon module or a detector. And I have one in my hand. If you want to see, you're welcome to come after the talk. See the real thing. So, and we put a flag here because that a quarter of the sensor is actually built in Taiwan and then shipped to CERN for the further production. And so once you have a module, you try to build it as a bigger module, and you put in more sophisticated electronics. These are all also built in Taiwan, actually by our group in NTU. And then once you put everything together, form a plan, then you become a real big detectors. Okay, and I just want to mention that since this is a strict detector, that means you only have a good resolution on one axis, not this direction. So what we do is we build two layers and then segment them differently. So in the first layer, we segment that have a better resolution on X, and the backplane you rotate 90 degrees, so you can measure the Y. So it's effectively a three-dimensional measurement because you also need to know where it plays, so you have the Z coordinates as well. And yeah, just a little bit of history that once you put the thing together and then you install it in the CMS. This was back to 2008, 2009. I was here. Okay, and since then, the Taiwan group, meaning both NTU and NCU, has been leading or in charge of both operation and the data analysis. Especially NTU is in charge of online data taking, while NCU is on data quality monitoring. And once you have detector, of course, you try to run it, try to understand it. This is the example that the preparing the detector to be used. This is the calibration. This is the what we call minimum analyzing particles. So you take the real experiment data. You see where the MIP usually is muon, sometimes can be pions. That you see it should be a good Landau, and since we know what the MIP is, you can calibrate your detector to very good energy resolution, better than 5%. 5% because it's sampling calorimeter, you cannot reach 1%. And we also do the alignment, and for example, this is hit on track efficiency as function of track transverse momentum. You see very nice agreement between data and Monte Carlo. And the reason it's not reaching 2% is the scattering right before the preshower because of material. But it's well predicted by Monte Carlo. And once you know everything, you start building even higher level where we actually build the single photon pi-zero separation identification variables that is used for Higgs gamma-gamma analysis, which I will also mention a bit later. And then the next project, so since preshower is ESO, we have the second project is the phase 1 pixel detector, where we go from end cap to the inner barrel. And so here shows you the drawing of the phase 0, which had 3 layers, to the phase 1 pixel detector that has 4 layers. And also we can see the first layer is actually very close to V-type now. Okay. And or if you look at the R5 plot, the Z, sorry, RZ plot, you can see this is the old detector, this is the new, and not only you have one more layer, we also have more end-cap modules. So we went from 60 million channels to 125 million channels. Sorry. And so the barrel, I just want to mention that the four barrel layers are produced in 5 production centers, and the end-cap is produced in the US, and one of the production centers is led by me and Dr. Anna Heiser at CERN, so that we collaborate with CERN technicians, engineers, and the Helsinki group of people. Okay, and what is a phase 1 pixel detector? So slightly different than the preshower. This one is use the technology called hybrid silicon detector. That means you have 2 silicon pieces. One as a sensor, measure the charge and Hall creation, and then again absorb in the cathode anode on the side. But instead of pulling out the signal, you do a direct bonding. On top, you have a readout chip and electronics. This bonding is what we call micro bonding. The both size is only 20 micron, which is not easily achieved by commercial yet. Okay, and this is a picture of a pixel module, which is this dimension. I happen to also have one. If you want to see, you can see what the pixel module looks like. And yeah, I just mentioned that our funding is supported by the academic summit project. And a few pictures, just have you go through how the detector was built for the pixel module. Everything is happening in a clean room. So what we do is the mechanical alignment and assembly using the precise jigs that you, for example, you prepare alignment jigs to have the sensor visual inspection, attaching the glue on the base strip, and then stamp on it and wait for 24 hours to be cured. After that, you check the alignment. And for example, here's the glue stamp. So if you want to glue two things together, what do? You don't just scratch the glue on top of it and then put them together, because the glue goes everywhere and you're on the sample. So you have to design a pattern that match your sample. For example, you can see all these dots and there's opening that has no glue. So even the stem is designed by several iterations that you don't destroy your prototypes. And you use dots because then once you squeeze or contact two samples, you smooth out and connect all the glue down together to become a film. Okay, so this is the second steps. Once you have the glue, what we call bare module, you attach HDI, which is flex circuit. It's like PCB, but not based on G10. It's based on the flex Kapton. So you prepare glue, check the alignment, and then stamp on it, and then place the HDI on top of the silicon. Wait for 24 hours. Okay, and then I'll just say a little bit on how we do, how we examine the detectors. Of course, you do the basic on-chip characteristic tests, or like inject the internal pulse. But one thing interesting is that you can actually shine the X-ray on top of the detector sensor and measure detector. So that's already a physics. So what we do is we use 4 targets, zinc, molybdenum, silver, and tin. And then they also have the K-alpha characteristic line that is showing, for example, on these 4 spectrons. Then by measuring the linearity, you can measure or calibrate detectors. And here's just a picture that you put the 2 modules inside the X-ray box, and then you create the lights. The other one is to see if your detector is efficient still in the high range. So instead of using the secondary, we put the module directly in the X-ray, direct X-ray line. So we can measure up to even 200 megahertz per square centimeter. And then you see that very good efficiency curve, even up to 250 megahertz. And this is expected at that time, you will see a couple %. And by doing that, you can already, you got also very nice tomography photos. And every component that you can match with, like connector here, there's a chip here, blocking, and all the capacitors on the side. Okay, and then the other thing is that in the beginning of the project, what you do is another particle test, which we build 8 layers of using the single chip and rock, and put it under the beam to do a beam test. And this is an example of one event for inside 120 GeV proton beams. You see actually there are 4 particles in this packet, so you can reconstruct them and measure the efficiency as well. And this is very important that we had several TestBeam happened that we measure and then feedback to the feedback to the rock designers. Then actually we had the bug fix and some improvement had to be made. A new version of rock that sample readout chip was produced. Okay, let me go to the phase 2. So phase 1 was built. Actually, the module was produced. The module production was done in the summer last year, and so now we're talking about phase 2. So again, phase 2, we're talking about 2023. There will be 3 parts. The first, still, if you want to have the EM part in the front, so you can precisely measure the electron and photon. There will be 28 layers of either lead or tungsten or copper or combination of the material, followed by silicon sensors. That 25 radiation lens should absorb most of the photon in electrons. Then there will be 2 hadron detectors that we call the front of the hadron that is sandwiched by the brass as absorber, and then the silicon, the same silicon design, and the back hadron will be brass and singulator. And we are aiming to have the Taiwan CMS team working together and to build a production center. Actually, we already have a startup funding for the R&D, which led by Stasis, that we aim for even general purpose of the silicon project, so that is not CMS only. So you see that academic silicon and Tsinghua University also part of that. Okay. And the design layout, quickly go to that, is we have 3 different thickness of silicon, and the reason is that this, if you go to the inner radius, the radiation environment will be harsh, so you want to have a thinner silicon so you can maintain the good performance. And we'll choose the NEP type sensor instead of P-on-N, as I showed earlier. The reason is simply that you can have better performance with high radiation, and also N-type is found to be a problem with the shot noise. Okay, so here is the a sample of one of the sensor. So the sensor is a bit non-traditional shape. It's hexagon. Even the pad is hexagon, not strip or pixel square anymore. And we have at hand is the Hamamatsu 6-inch, and we have tested different thickness. They all have very good quality performance, but we aim for the 8-inch sensor because it's cost efficient and we have a fewer modules. Now the vendor is E3. Actually, we are also aiming to see if we can produce some in Taiwan as well. So that part is is under investigation. Just a few words on front-end electronics. I'll probably not be going through detail. So the readout will be digital, and so all the charge we collect by silicon will be converted to digital, like the charge size or time on the threshold. And it should be designed to absorb a lot of charge. And the chip actually, this is a new development. So CERN has signed the current contract with Haijidian. So all the new chip phase 2 will be done here in Taiwan. That's why I think one of the advantages that if we have a production center and expertise in Taiwan, we can have the first-hand communication with Haijidian people. And the test vehicle has already been submitted, and we have people testing them, and so far it looks very good. And we are collaborating with the CALIS group, which is for the linear collider group, because they have some design, and we have used actually their chip for the TestBeam last year, and for the 2017. There's a new version, Skyrock 2 CMS, that is specially designed for us. Actually, we have that in hand. We're testing them, and then